this chapter, we're going to start looking at applications of derivatives. In this lesson, we are going to start looking at related rates.
All right, hi everybody. So we're going to take a look at another application of derivatives, this time called related rates. Okay. Now, what this is, if I can give you kind of just a little explanation before we get into a bunch of examples, because really that's what we're going to do. I'm just going to start to show you a bunch of examples. But what the idea is that a lot of the things that we deal with in the real world are dynamic. But the math that you've done up to this point has been very static. For example, you might measure a wall. Let's say you're going to determine whether or not a wall is perpendicular to the floor. So maybe you measure up 3 meters, or let's say 3 feet. Then from the floor you measure out 4 feet, and then you're going to connect those 2 points with, let's say, a string. If that string is 5 feet, okay, then you know that you got that Pythagorean triplet. You know that that wall is perpendicular to the floor. But nothing's moving there. It's all very static here. Calculus allows us to look at what happens when something changes there. And I'll give you a very similar sort of situation. Let's say that you've got a car driving down the road, and you've got a policeman standing off to the side with a radar gun. Well, the car isn't driving towards the policeman. The car is driving beside the policeman. Okay? But the radar gun measures the distance along the hypotenuse, not the distance along the road, or I should say the speed. Okay? Calculus allows us to make calculations like that, to see how one variable affects another, or I should say the change in one variable affects the change in another. But we start it by building equations that you are already familiar with, and that's the beautiful thing about it. Calculus isn't about building these equations. You can build these equations, these static equations that you're used to already, and we'll use calculus to transform them. So, for example, a stone is thrown in a puddle and its ripples spread out in circles, the radii of which grow at a rate of 4 centimeters per second. Now, right there, that's a rate. Okay, I'm giving you a rate. I'm actually giving you, that's a derivative right there. Now, we want to find the rate of increase of the area of the circular ripple when its radius is 20 centimeters. So let's just draw this out here. So we've got this circle, okay, because we've dropped our stone in there, and that ripple is moving outwards. Now, here's our radius. Now, we just said here that the radius is growing at a rate of 4 centimeters per second. So what we know here is that the derivative of r with respect to time, the rate of change of r with respect to time, is going to be positive 4 centimeters per second. Now, just a little note here, positive because it's increasing, okay? The value of the radius is getting larger, so its rate of change is positive, and that should imply what would happen if it was negative. If it was negative, it would be getting smaller, which doesn't make sense in this context. Now, granted, you can define that to be different, but this, I think, is the most natural way to read that. We are looking for the rate of increase of the area, okay? So we are looking for dA by dt. I don't know what that is, okay? And we're given a very specific bit of information here. We're looking for that rate of change at the moment the radius is 20 centimeters. Okay, so at the exact moment we've got 20 centimeters here. Now, I'm going to show you how to do this, okay? And what I'm going to do is I'm going to show you something incorrect first, just so that it's out there, we state it right away, what not to do, and I'll show you exactly why. Now, first of all, I want the rate of change of area. I'm given the rate of change of radius. So what I would like, before I get to the rate of change, I would like a relationship between area and radius. And I know that that relationship is going to be area is equal to pi r squared. Okay, so there's my relationship. Now, the incorrect thing to do. Okay, so we're going to put a little star here. This is incorrect. What is very tempting to do here, but this is incorrect, is to say, well, we know that the radius is 20. We're looking for at the moment the radius is 20. So this is going to be pi times 20 squared. That's 400. So 400 pi. Area is equal to 400 pi. Wonderful. Now, You think, well, it's a calculus class. Let's take the derivative. So dA by dt is equal to, well, 400 times pi is just a constant. And I know that the derivative of a constant is 0. And so there we go. What's the rate of change of area with respect to time? 0. I didn't even need to use the radius, the rate of change of radius. Move on to the next question. Well, that is incorrect. Okay, that is incorrect. What I want you to note here, big note, okay, do not substitute in values of a variable prior to taking the derivative. Okay, that is worth taking a couple seconds and writing down. Do not substitute in values of a variable prior to taking the derivative. Okay, now, that being said, you may substitute in values of a constant prior to taking the derivative. And in fact, you should. And we will take a look at examples of both of these. I mean, this one right here immediately is a good example of a question where you don't want to plug in the value of the variable prior to taking the derivative. So let's finish this off here. So variables, do not plug in, okay, do not plug in values. But if it's a constant, if you know that you've got an equation here and this variable here or this letter could be a variable, it could change in time, but in this particular context, it doesn't, then you can plug in that value. But if it's a variable, if it's something that changes in time, do not plug it in, because what will happen is exactly what happened here. You'll take the derivative, everything goes away. Here's the correct way to do it. You've got area is equal to pi r squared. Well, let's take the derivative of that expression there, that equation. And bear in mind that I am taking the derivative with respect to time. Time is the independent variable here. It's not a, it's not r, it's t. And so notice that t does not show up in this equation, so I'm going to have to take the derivative implicitly. So that means dA by dt is going to equal, I'm going to bring the 2 down, so 2 pi r dr by dt. Okay, so I know r is some function of time. I don't know what it is, but I took the derivative of the outer square, and now I got to multiply by the derivative of what's inside there. Now, I would be a horrible teacher if I did not point out something really cool that just happened. Take a look. There's our area. Okay, that's our area function right there. Notice when I took the derivative, look at that. 2 pi r, that's circumference. Take the derivative of area, got circumference. That is not a coincidence. And we will come back to that later on in this course, but it is worth pointing that out right now. That is a really neat result. Anyway, let's keep going here. We are looking for dA by dt. I know, now that I've taken the derivative, now I can plug in the values of the variable there. So I know that r is 20, and I know that dr by dt is 4. And see, if I wait till after the derivative to plug in these values, then I have the dr by dt there. Okay, so what have I got here? I've got 2 times 4 is 8, times 20 will be 160. So the answer here is 160 pi, and whatever our units are, centimeters squared per second. And actually, centimeters squared makes sense because this variable right here will have units of centimeters. This one will be centimeters per second, and so there it is, there, centimeters squared per second. Okay, so the math here should correspond to the physics of the problem or the geometry of the problem as well. So that gives you a little bit of an introduction to this. What we're going to do from this point on is we're going to just go through example after example after example. In fact, the next few video lessons that you'll see here, that's really all we're going to do, is just I want to give you a bunch of examples to look at. All right, here's our next one. A spherical balloon is inflated so that its radius increases at a rate of 2 centimeters per second. Okay. So right there, we've got a rate, a derivative. So before I even get into the problem here, I know that dr by dt is going to equal 2 centimeters per second. Okay. I want to find the rate of change of its volume, so I am looking for dv by dt. Okay, and you're going to notice that when I go through and do this, a lot of times what I do is I'm putting off what I know off to the side. So I mean, you might even put a little, column here. I know dr by dt, and I know that I'm looking for dv by dt. Okay, these are the things that I need, or I know that I need. Okay, now in the first scenario here, A, I'm asking for this when the diameter is 30 centimeters. Okay, so in A here, the diameter is 30 centimeters. Well, what am I saying when I tell you that the diameter is 30? What I'm telling you is that the radius is 15 centimeters. Okay, now, and then I've got another one here where I give you the surface area, and we're going to come back to that in just a moment. Let's talk about that first one. So here we go. Here's our spherical balloon. I know the radius is getting larger at 2 centimeters per second. What I need is dv by dt. So to get a relationship between the rate of change of volume and the rate of change of radius, I need an equation that relates volume to radius. Okay, and the volume of a sphere is 4/3 pi r cubed. Good. Now, remember, don't plug in the 15 right away. This r is a variable. R is changing in time. I need to keep the value out so that I can get the derivative of r popping out there, the dr by dt. If I plug in that 15, that won't happen. It'll just be a constant on the other side here. But I've got this nice relationship now between v and r. I can take the derivative. So dv by dt is going to equal, 4/3 pi, and this will be 3r squared. Remember, the independent variable is time, not radius. That's the derivative of the cube. Now I got to take the derivative of what was inside there, that r. So dr by dt. Okay, and there's our derivative here. Now, I'm going to simplify that just a little bit. There's really not much to do here, but I have a 3 in the numerator, the 3 in the denominator, and that'll get me 4 pi r squared dr by dt. And once again, I would be a bad person if I didn't point out, look at that. Look at that. Volume, okay, this is the volume of a sphere. 4 pi r squared is the surface area of a sphere. Okay, I don't care who you are. That was cool. That is neat that happened there. And again, we'll explore that relationship a lot more deeply later on in the course here. Okay, so here's my dv by dt. Okay, that's what I'm looking for. I've now got this expression in terms of r and dr by dt, so now I can start plugging things in. 4 pi r is 15, so 4 pi r squared. And dr by dt was 2. Okay, so to simplify that, we got 15 squared, which is going to be 225 times 8, really. And so this will become 1800 pi centimeters cubed per second. Okay, centimeters cubed per second. And that, again, that makes sense because the r is going to give me centimeters squared, and dr by dt will include another centimeters per second. Okay, and you'll notice that we don't often multiply that out. We'll just leave it as 1800 pi. That's fine. Second half of this problem said, well, what if the surface area was 676 pi centimeters squared? Now, let's think about that. Why would they tell us that? What is it that I actually need to get dv by dt? Well, if you look at the previous question, what I needed was dr by dt, and I've got that, but I also needed the r. So I'm not giving you the r here, I'm giving you the area, but that's the link. Okay, I know that area is also going to equal 4 pi r squared. Okay, so what I'll do here is I will solve for r in this case. So I'm going to divide both sides here by 4 and by pi, and I will get 169 is equal to r squared. Okay, and we know that the square root of 169 is going to be 13. Now, normally, we would write plus or minus 13, but I think the context is clear enough that we know that r is simply going to equal positive 13. Now, truth be told, I didn't even really need to do that. Okay, and I'll show you why in just a second. Now, that is a very natural thing for us to do, but I didn't need to. So let's go back up to this. We've got volume is equal to 4/3 pi r squared, pi r cubed. I'm already anticipating where this is going to go. I want to take the derivative, so dv by dt. Bring down the 3's will cancel, so 4 pi r squared dr by dt. And you might even at this point notice why I didn't actually need to get the radius. All I needed was radius squared, because that's what's in the derivative here, is this r squared. So now I can pull it in here, 4 pi, and I'll just put in 169, because I know that's what r squared is going to be. And dr by dt was 2, so 169 times 8 will be 1,352. This will be centimeters cubed per second. Okay, there you go. All right, another problem here. A weather balloon with a radius of 12 meters develops a leak. Okay, losing air at a rate, there we go, a rate of 24 pi meters cubed per minute. Okay, that right there, if you want to identify the things that we know, that right there is a change in volume. Now, it's losing air at a rate of 24 pi meters cubed per minute. So that would be negative 24 pi meters cubed per minute. Good. We want to find the rate of decrease of the radius. So this is another thing we know. We know we're looking for dr by dt. Don't know what that is. After 4 minutes, we know that the time is going to be 4 minutes. Now, there was one other bit of information that we were given here, and that was initially the weather balloon with a radius of 12 meters develops a leak. So we know initially, okay, and I'll use that as Ri, the initial radius is going to be 12 meters. Okay, that's huge, hey? Those weather balloons are just gigantic. 12-meter radius, 24-meter diameter, that's huge. Anyway, so we want to figure out what dr by dt is after 4 minutes. Okay, well, I need a relationship between r and v. Okay, and we've already gone through this in a previous question. We know that the volume of a sphere, and we have to assume it's a sphere in this case, okay, it's going to be 4/3 pi r cubed. We're going to take the derivative with respect to the independent variable t, which means taking the derivative of this implicitly. So we bring down the 3. It's going to cancel with that denominator. So 4 pi r squared dr by dt. Once again, always amazed when the volume becomes that surface area. It's really cool. I know what dv by dt is. It's negative 24 pi. I don't know the radius at 4 minutes. I'm looking for dr by dt. So right now, I am okay with dr by dt being an unknown. It's that r that I'm a little bit concerned about, okay? Because I need the radius at the 4-minute mark to figure this out. Okay, so now how am I going to go about doing this? Okay, I need to figure out what the radius is at that 4-minute mark, and all I know is what the radius is at the beginning. But I do know that it's losing air at 24 pi meters cubed per minute. So, okay, so here's what I got to do. I will come back to that in a second. I got to do a little bit of work here to figure out what that new radius is. So, first of all, what's my initial volume? Where did I start? Well, 4/3 pi Ri cubed. Okay, so that's going to be 4/3 pi 12 cubed. So I'm just going to figure this out here. 4 divided by 3 times 12 cubed. So my initial volume is 2,304 pi, okay, meters cubed. Now, in 4 minutes, okay, in 4 minutes, I lose 4 times 24 pi, okay, 4 times 24 pi meters cubed per minute, which means I've lost 96 meters cubed. Oh, sorry, 96 pi. My mistake. I forgot about the pi in there. I got it. Can't forget about the pi. Okay, that's 96 pi meters cubed. So the final volume is going to be 2,304 pi minus 96 pi. So 2,300. I'm going to do this on my calculator because I don't want to do it in my head and get it wrong. Which means my final volume is going to be 2,208 pi meters cubed. Okay, good. That's my final volume. I'm going to use that to figure out what my radius is. So remember, volume is equal to 4/3 pi r cubed, and so the final will equal final radius. So 2,208 pi is going to equal 4/3 pi r cubed. So I'm going to take that 2,208. Now, by the way, the pi's will cancel. So I'm going to multiply that by 3, divide by 4. I'm going to get 1656 is equal to r cubed. I would be a little shocked if that worked out nicely. And it doesn't. Okay, and it doesn't. So what I'm going to do here is I'm basically going to take this as the cube root of 1656. Let that equal r. Whoops. That could be positive or, sorry, my mistake. It's a cube root, not a square root. So that would be positive, cube root of 1656. Now I'm just going to see if I can simplify that a little bit here. Okay, I can in fact take out a common, an 8 there, so make this 2 times the cube root of 207. Okay, it's always good to reduce this as much as we can. Actually, that's about as nice as that's going to get. Okay, went a little bit further there on my calculator, but that is about as nice as that's going to get. Anyway, that's neither here nor there. We finally got the radius down. We're good. Let's take it and go back up. 2 times the cube root of 207. So we come up here. We know that our dv by dt is negative 24 pi. We know that this is going to be 4 pi. We know now that the radius is 2 times the cube root of 207 dr by dt. Now, the pi's will cancel, and I'm going to be left with, the pi's will cancel, negative 24 divided by 8. Oh, sorry, my mistake. That should be squared. I forgot. Ooh, that would have been bad. I forgot to square that. So that's going to end up being, when I divide that over, this is going to end up being, I'll divide by 4 first, so negative 6 over, and that is going to be 4 cube root of 207 squared equals dr by dt. Actually, that can be simplified a bit, but I don't even know if that's necessarily worth it. Well, okay. Yeah, I'm just going to write down the numeric value here because that's starting to get a little wonky. So that is going to be the cube root of 207 to the power of 1/3 squared. And so we're going to get negative 0.04 meters cubed. Oops, not meters cubed. Oh boy, I'm sorry. I'm all over the map in this last little bit here. Meters per minute. Not meters cubed per minute, because we're not talking about volume anymore. We've gone backwards. We're going back to radius there. So yeah. Again, I could have simplified that, but that actually works out a little bit nicer. That looks better than what that answer would have looked like if I'd even tried to simplify that there. Okay. So anyway, a little bit more of a complicated problem because the value of the variable wasn't given directly to us. We had to go looking for it. Okay, so that's a good kind of a model for a question. Keep that in mind that this sort of thing does happen in these problems. Right. Our next question says a conical container is 30 inches high and the radius at its top is 6 inches. Okay. it is filled with water at a rate, oh, here we go, of 15 cubic inches per second. Okay, so what do we know? We know that dV by dt is going to equal 15 cubic inches per second. Now, positive because we're increasing, okay? Find the rate at which the water's depth, okay, let's call that height, dH by dt. Find the rate at which the water's height is changing when the height is 18 inches. Okay, at that specific moment, we get 18 inches. Okay, now this whole cone sort of question, everybody, this is a classic. We, as teachers, we go back to this one a lot because of the beautiful little relationship that pops out here. So here's our cone, okay? We need some sort of a relationship between the volume and the height of the cone. Well, the equation is this. Volume is equal to 1/3 pi r squared h. Now, there's my volume, there's my height. But I've got this other letter here, r. Now let's just think about this. As I'm pouring water into this, here's my water level. Okay, there's my height, there's my water level. Now, as I pour water in, the height changes. Does the radius change? Well, yeah, it does. The radius is also a variable in this scenario. Okay, so I can't just get rid of the radius. I am stuck with this radius in this problem because it is a variable. So what I would like to do is, if I can, rewrite r in terms of h. So what I'm looking for here is some sort of dependence of r on h, because if I can plug that in, substitute that in for r, not a value, okay, not a number, but some sort of a relationship, then I can use that, and if I take the derivative of that, I'll be fine. Now, actually, it turns out in these cone questions, there is a beautiful relationship that's just kind of waiting there for us to use, and that is this. The height of this cone was 30 inches, and the radius at its top was 6 inches. See, but what's nice about that is that this r right here and this height, okay, form this right angle triangle right here, which is similar to that large right angle triangle. So I know, based on that, okay, that radius to height of the whole conical little container here should be equal to the radius to height of the water, that basically that conical bit of water right there. And so I can use that to do a substitution here. Now I can tell right now 6 over 30 is going to be 1 over 5. And so r is always, whoops, sorry, can't see that. R is always going to equal 1/5 the height. Well, now I've got a nice relationship between r and h that I can go back to my equation here, and I can make this a little bit more specifically between h and v. And so now this will be 1/3 pi. This is going to be h squared over 25 times h. Okay, and it doesn't take much to see that this is now going to become pi h cubed over 75. And so that is the relationship between volume and the height or the depth of the water that I've been looking for. Now, this is not the only way to approach a problem like this. We could have taken the derivative with r being a variable and basically just applying the product rule here and multiplying that all out. We would still have needed this relationship though, okay? But we could have applied it a little bit differently, and you will see later on in these examples. We'll take a look at an example where that's really how we approach it. But this is a little bit nicer. It's a little bit cleaner doing it this way. So now I'm going to take the derivative, because I'm going to take this static equation, we're going to change it into one where we're talking about how these variables change. So remember, time is the independent variable, so I'm going to bring down the 3, so 3 pi h squared over 75, and then I have to multiply by the derivative of h with respect to time. Okay, so dv by dt, I'm just going to simplify this a little bit because I can make this pi h squared over 25 dh by dt. All right, now I know that the volume is increasing at a rate of 15 inches cubed per second. I know that my height is going to be 18. Okay, and so now this will become 15 multiplied by 25 over 18 squared pi is going to equal dH by dt. Now I'm just going to clean that up a little bit with my calculator. 15 times 25 divided by 18 squared. Well, that doesn't clean up all that much actually. So this becomes 125 over 108 pi. And this is going to be inch. Now remember, this is dH by dt, so this is just going to be inches per second. And that is the rate at which my height is changing. And again, that makes sense because I've got dV by dt is going to be inches cubed per second, and I'm going to divide right here by an inches squared. So it makes sense that I'd be left with inches per second there. Okay? Anyway, that cone question, that is a classic. And there are a few, and I will point them out as we go through. These are the sorts of questions you're going to do over and over and over again. They'll change the scenario a bit, but the idea stays the same. Okay, another question related to spheres. A spherical crystal is growing at a rate of 1 cubic millimeter per minute. Spherical crystal is growing at a rate of 1 cubic millimeter per minute. Now that's a volume rate right there. So what do we know? We know that dV by dt is going to equal a positive because it's growing. Okay, 1 cubic millimeter. Okay, 1 cubic millimeter per minute. Okay, we want to find the rate at which the radius is changing. So we are looking for dr by dt. Don't know what that is, but we're looking for it at the specific moment when the surface area is 8 pi. So my surface area, 8 pi centimeters squared. Now, see, I need a relationship between radius and volume, and I already know what that is. Okay, I know that my formula here will be 4/3 pi r cubed. I got that. But that extra bit of information I'm given is not in terms of radius, it's area here. So when I take the derivative, dV by dt, and again I'm doing it implicitly, I'm going to keep saying that, okay, we bring down the 3, so it becomes 4 pi r squared dr by dt. So I'm looking for dr by dt, that's the unknown that I'm really looking for. I have dV by dt, but I've got this extra variable r in there that I need. But I gave you this information, so really what I need to do is I need to extract from this what the radius is at that moment. So I kind of got to take a little bit of a sidestep here and say, okay, I know that area, the surface area of a sphere is going to be 4 pi r squared. So if I plug in that 8 pi, 4 pi r squared, if I divide, I'm going to get 2 is equal to r squared. And actually, you know what? I'm not going to solve for r. We had a question like this before. I could have gone through and gotten, okay, r is equal to root 2. But that's really all I needed because I've got r squared up here. So dV by dt is 1, 4 pi times 2, and I'm looking for dr by dt. Now, I didn't say it in the last one here, but I want to mention this again. Remember, don't plug in those values. Don't plug them in early. Don't plug in the values of variables prior to taking the derivative. Always plug in those values after you've taken the derivative. Okay, and so we're going to get 8 pi here. So when I bring that over, I'm going to get 1 over 8 pi. And what is this? This is going to be centimeters, what is that, per minute. That's how fast the radius is changing. Okay, 1 over 8 pi centimeters per minute. And again, that makes sense because the units for the change in volume will be cubic. I'm going to divide by that radius squared, so I'm going to be left with that single unit there, centimeters. Okay, I hope that makes sense.